So the DFT uses this function. This is a root of unity. So let's demonstrate that. So imagine we have the equation x to the n equals 1. Then we could equally write x to the n is e to the 2 pi I lots of n, where n can be any integer because all of this will just be multiples of 2 pi lots around the argand plane. So therefore x is e to the 2 pi I n over n. So if we consider just when n is equal to 1, then this will represent just a little angle 2 pi over n. And then n equals 2, etc. n equals nothing is of course this point, and n equals n minus 1 would be here. So we are stepping through with angles around the unit circle with this function. And of course if it was minus, it would simply be stepping the other way round. It's periodic, so clearly this point occurs when either n equals 0 or n equals n or n equals 2n, etc. But this point would occur when n equals 1 or n equals n plus 1, etc., or 2n plus 1. Just demonstrating that. So it would be 2 pi I n plus 1 over n, which is 2 pi I plus 2 pi I over n. So we've done one lap round, one lap, and we've come back where I started. In fact, going this way, these should all be negative. That's an error. I think that's clear. So this means, now with my DFT, we are building something by adding together these functions over k. So we're changing k. Now all that means, let's look at the effect of k now. So so we have the function as e to the minus 2 pi I n over n, and this is just the nth root of unity times k. So when k equals nothing, everything is 1. So this function is just a series of 1s for all values of n. When k equals 1, now what we now have is we are stepping around the unit circle with angles of 2 pi over n. So that's, this point would be 2 pi over n, then it would be 2 lots of 2 pi over n, etc., etc., until we get to that point. So this is, so we do one rotation around the unit circle, and then we'll carry on doing another rotation, etc., etc. But basically within the sort of 0 to n minus 1, we would do one rotation. So this is the slowest journey around the unit circle that we can do. So that k equals 1 is the lowest frequency. K equals 2, on the other hand, is going to be doing 2 steps at a time. So this is going to be twice as fast, so twice the frequency. So the 2 rotations. K equals 3 will be doing 3 of these slabs, these angles of the root of unity. So it will be 3 times faster than the k equals 1. So in some sense the k equals 1, if this has angular velocity omega, this will have angular velocity 2 omega, 3 omega. So this is sort of like a harmonic. And then we're going to get to, as we continue, eventually we get to the maximum, which is n minus 1 in this, which means it's going to do n minus 1 slabs. It's going to end up here. So it would have covered all of that distance to get to this point. So this is going to go round and round with an angular velocity of n minus 1 omega. So this is the fastest. Then of course, if I have the next one, if k was equal to n, I just end up where I started. And so basically that's the same as having exactly the same thing as k was nothing. In other words, k equals n will be the same, have the same pattern as k equals nothing. And this is important because this is aliasing. And we can actually see as well that k equals n minus 1, going around like that, has the same effect as k having a negative frequency of minus 1. These two frequencies are the same. The only place where, so a high positive frequency has the same effect as a low negative frequency because they have the same root of unity. They don't have the same root of unity, but the effect along the perimeter of the unit circle is the same. So this essentially means we don't get this duplication up to the halfway point. So up to the halfway point where k equals n over 2, at that point we don't get this well, we do get a duplication, but if we we could uniquely define a range, if you like, that we can be sure there isn't any duplication. So we could go from, say, so for example, if we have a root of unity which is a quarter of a circle, then we could identify these points like that. If it's even, then we're always spread out in this way, and if it's odd, then we're always spread out, so we sort of miss the halfway point. Now my understanding is the halfway point is the Nyquist frequency. So essentially these are the only, this is the maximum frequency that you can find without there being aliasing. Although I'm not entirely sure about it, but that's just the largest frequency in the signal that can uniquely be determined. I suppose that would sort of make sense. If you have a higher frequency than that, then you would have negative frequencies and positive frequencies both. Well, I'm not sure about that. Right. So, but suffice to say, this makes it very clear that these harmonic functions are stepping through chunks, slices, based on the nth root of unity. And because they're all sort of every iteration, every epoch, we do our step. The ones with higher k values go through a bigger step. So what we have is a large number of rotating objects. Some objects rotate, some objects not rotating at all, some objects rotating twice the speed as the previous ones, some objects rotating 3 times the speed of the previous, until we get to an object that's rotating n minus 1 times the speed of the previous one. And each of these rotating objects are just adding phase, because that's all they do, they're just adding phase. They're adding phase to whatever the number is, multiplying them, and then we're adding them together to make a gigantic total. So this is the bare bones of it, is we have these rotating objects, and each one is multiplying by a complex number to generate a total. Right. The next thing, which is quite interesting, is the following. If you remember the definition of the DFT is xk is sigma n equals nothing to n minus 1, xn e to the x 2 pi I kn over n. So this is just adding together these harmonic functions, and it gives us our frequency bins. So we can regard each, so these are these are both sequences of n complex numbers. So we are actually in a space of discrete sequences of n complex numbers. Let's call it c to the power n, although it isn't really that. Now what we are doing here is we have these these bases, these axes, that, so one of them would be just 1, 1, 1, 1, like that. That's, and then we have the next one, which would be that whatever the fundamental frequency is. So n equals nothing, k equals 1 rather. Now n equals not, if k equals 1, yeah, so we still get nothing, omega, omega squared, blah 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 blah, omega to n minus 1. So it'll be another direction, and then we have another one which is nothing, omega squared, omega 4, blah 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 blah. Right, so the point is that each of these directions, these are vectors, and we are adding weights to each of those to get, so every sequence could be expressed as a weighted sum of these harmonic vectors in this space, in this linear space. So this is essentially what my DFT is doing. It is transforming into a set of axes where each axis is given by this. And this will correspond to the degree of correlation with this. The other thing, just to point out, is that it is obvious that if I was to take omega and I sum it with omega star, that this and I do that point by point, then each of these is going to be the modulus of omega squared. So this is going to be n. So we could just do 1 over n in order to normalize that to make sure that's 1. Alright, so quick summary then of where we're getting to so far. The goal is to increase sort of intuition and understanding about the discrete Fourier series, discrete Fourier transform. So we're looking at this harmonics, the harmonic function. We have shown that it's nothing more than the nth root of unity, which is these little slices. So it's worth saying that therefore that the size of these slices depends entirely on how many steps we have in the sequence. So it might not actually be very good for spectral analysis. So we have, now depending on k changes the rate of rotation around this circle. So that's the next point. So each of these are spinning disks, spinning at different frequencies all being integer multiples of the fundamental frequency, which is omega. That was the first point, and the second point being the relation between the positive frequencies and the negative frequencies. So all of our positive frequencies could be expressed as negative frequencies, and since they are nth roots of unity, it's all going to be periodic. So any sequence we get, it's going to be periodic, infinitely repeating sequences that we're generating. And then we looked at the more abstract way of viewing it, which is that we essentially have, we're essentially adding together not sure this is entirely correct actually, but looking at this, we're adding together these functions with these coefficients. So this needs to be thought out more carefully, but in some senses, yeah, I think this is wrong. This is wrong. Okay.